Hello and welcome to this BioProcess International Ask the Expert webcast. I'm your host, Leah Rosen, the online editor for BioProcess International. Before we get started, just a couple of notes. This webcast is being recorded and will be made available for replay in the multimedia section of our website. We've muted the audio lines, but we welcome you to type in your questions for our speaker in the question and answer window on your screen. After the presentation, we will begin the question and answer portion, and I will ask our speaker your questions. Your questions in the question and answer window will only be visible to myself and our speakers. So thank you for joining us today. It is now my pleasure to introduce our speakers, Andy Ambroso and Cristina Bernal Martinez from Getinge, to share about Applikon bioreactors.
Thank you, Leah, and thank you everyone for joining us today. One of the most challenging aspects in upstream bioprocessing is to start from cells growing in plates or flasks and then determine process conditions in a bioreactor. And then once a working process is in place, transferring that process into a larger scale can also be stressful. Applikon is well known for high-quality glass autoclavables and steel bioreactors, and in recent years we've applied that expertise to produce the Applikon ST, a single-use bioreactor at bench scale. Today I will briefly discuss the fundamental principles in bioreactor scale-up so you can see how to put these ideas into practice with single-use stirred tank vessels. First, it is important that the Applikon has the classic hemispherical shaped bottom, which enables well-mixed liquid culture conditions. Next, 3D printed parts make it easy to copy the shape and geometry of the stirring assembly and other head plate components in our glass vessel. And with this starting point, well-known scale-up considerations can aid in transferring a process between different sized bioreactors. So as we start to look at the theory of scale-up, it's important to create similarity of geometric and physical influencing variables. From there, a scale-up strategy will rely on creating a single numerical value that represents the similarity, which is most important to your process. As I mentioned on the previous slide, geometric constants, such as height over diameter, illustrated here, can be accommodated in vessel design or perhaps by targeting specific working volumes in the scale-up vessels. But furthermore, it's important to consider the nature and morphology of the culture itself so that the correct scale-up constant is chosen. For example, the volumetric oxygen transfer coefficient, KLA, is important in aerobic systems where oxygen availability is important. Power per unit liquid volume, or P over V, relates to the homogenization and gas-liquid transfer, and it can also relate to shear stress. However, tip speed is most commonly considered if shear stress is the largest concern. So let's take a closer look. If oxygen transfer is the key parameter, then KLA is a good scaling factor. As you can see in this equation for oxygen transfer rate, there are two terms. All the way on the right is the term showing the difference between the equilibrium concentration of oxygen and the current concentration of oxygen, which I like to think of as the driving force in that concentration difference. The other term in the equation is the KLA, and this really encompasses all the other physical factors which are influencing oxygen transfer within the vessel. It can be affected by stirring speed, gassing rate, working volume, or even media composition. So with these many factors, it's most common to determine KLA experimentally using the static gassing out with nitrogen method. So you can see we've rewritten the equation a little bit such that the oxygen transfer rate, or the change in concentration, is equal to KLA, and then you have your C star, which by bioreactor norms is actually equal to 100% DO, and measured DO is the current C. We can then take the integral to solve the equation for KLA, such that when you graph the natural log of 100 minus the DO, you'll get a line where the slope is equal to KLA. However, this only tells you the KLA for one condition. It is possible to study the KLA rates for several conditions in your scale of interest or at the large scale, and subsequently model the effect that stirring or gassing has. But for the purposes of time, I won't go further in that today, but I'd be happy to address that if you wanted to follow up with us after this talk. So please reach out more with the contact info you see at the end. But let's take a look at another scaling constant if oxygen transfer is not the most important thing for you. In that case, you might want to use P over V. P over V is commonly used to match power input for mixing at different scales. And as we walk through this equation, you'll see that the power input to a bioreactor depends on many things. First is the power number of the impeller, which is typically obtained from the manufacturer. Next is the density, which is often assumed to be equal or close to 1. Then you have N, your stirring speed, which gets cubed in this equation, and then you have D, the diameter of the impeller, multiplied by the power of 5. The resulting power then gets divided by the working volume in the bioreactor or in the intended scale. So with the P over V calculated for one scale, you get a desired constant, and it's possible to subsequently calculate the stirring speed, which should be used in your next scale. Lastly, one more way to look at the stirring speed is by matching tip speed. Another way to scale the stirring speed is by matching tip speed. And the tip speed of the impeller blade is one of the locations where shear forces happen at the cells. So this can be really a good scaling factor when shear forces are your largest concern. As you see in the equation, tip speed is simply calculated by multiplying the diameter by pi and the stirring speed. And if the goal is to hold tip speed constant, what you see is that at a larger bioreactor, which would have a larger impeller, you will need to lower the stirring speed. I realize we have gone through these equations fairly quickly, but hopefully now you have some ideas how you could do scaling on your own, and you'll know the working volume of both scales, some parameters such as impeller diameter or maybe hopefully the impeller power number, and using some current stirring conditions, you can calculate one of the three values above and then solve for the unknown stirring speed in your new bioreactor scale. To see how this might work in a real-world example, let's listen to my colleague Cristina talk about a collaboration we've done with some of our customers.
Now, let's talk about blood cells and their cultivations in single-use stir tank bioreactors. There is a global demand of blood, and sometimes this fact faces important challenges, such as chronically transfused patients or situations in low-income countries. In this sense, the production of transfusion-ready erythrocytes from precursors is a potential alternative. But in this case, we will need to face more problems. So, problem number one is the large number of red blood cells required for a single transfusion. How can we face this problem? One solution could be the use of the stir tank bioreactors. Okay, let's say we decide to use the stir tank bioreactors. We will need to face another problem, the turbulence. Turbulence in the stir tank can cause shear stress and energy dissipation, which could damage the cells. In this regard, here we are going to present the results of erythroblast cultivation in stir tank bioreactors, in both single-use and conventional glass bioreactors. This work has been done together with the Delft University of Technology and the Blood Bank Sanquin in Amsterdam. The ex vivo expansion consisted of 14 days experiment. During the first 8 days, the stem cells were cultured in petri dishes until the differentiation to proerythroblasts. In that moment, those cells were transferred to the stir tank bioreactors, to the single-use and the conventional glass. For the next 6 days, those cells were cultured using a repeated batch as a mode of operation. In this slide, you can see how the repeated batch was performed. The cell concentration went from 1 million cells per ml to 2 million cells per ml every day. In that moment, some part of the medium is discarded and replaced by fresh medium to have again 1 million cells per ml. This process was performed during 6 days, and on the right you can see a graph where the cell concentration variation is shown during the run. This is shown in the mini bio and the Petri dish, but in the Applikon was also comparable to these two. Here on the right, you can see the theoretically calculated cumulative cell number that corresponds to the total number of cells that would have been produced if we would keep all cells in the bioreactor. It's calculated based on the number of cells that were produced each day in the reactor and the dilution factor, using for that the data of how much culture was harvested and how much fresh medium was added to the culture. To assess the state of the culture erythroblasts, the expression of the surface markers was determined by flow cytometry, as shown in Figure A. During proliferation, it's important to keep the maximum number of cells in gate P2 and P3, since P4 corresponds to spontaneous differentiation and should be kept at minimum. Erythroblasts expanded in glass and single-use stirred tank bioreactors presented similar erythroid surface marker after 6 days of culture compared to static conditions. And very important, lower number of spontaneously differentiated cells were observed in both bioreactors compared to Petri dishes. Terminal viability, measured as number of cells that are negative after propyrium iodide staining, was slightly higher in the single-use bioreactor cultures compared to glass bioreactor and culture dishes. You can see these results in Figure B. A step further was carried out with the expansion of the erythroblast. So we saw that we were able to keep the cells growing in the single-use 0.5 liter, and the aim of this experiment was to transfer those cells to a bigger sized bioreactor. To keep the same conditions and taking into account that these cells are very shear stress sensitive, we wanted to keep the same tip speed in order to get the same environment. The tip speed used was 0.3 meters per second in both bioreactors. So now the experiment is shown here in Figure A. During the first days, the stem cells were cultured in the Petri dishes, then were transferred to the 0.5 liter Applikon bioreactor, the single use, and after 3 days were transferred to the 3 liter. In Figure B, you can see the repeated batch as a mode of operation in the same way and was explained before in previous slides. Here in Figure C, you can see the evolution of the volume in the stirred tanks bioreactors. Started with 100 ml and at the end, the maximum volume of 2.5 liter was maintained. 3 biological replicates were performed thanks to 3 donors. And you can see here in those graphs, like the cumulative cell number, also calculated at the same way as explained before, was very comparable between the 3 donors in the bioreactor, and they show a bit of more variability in the static conditions. Erythroblasts expanded in the Applikon single-use bioreactors, graph A, presented similar expression of the erythroid differentiation surface markers compared to static conditions in graph B, and a very important, slightly lower level of spontaneous differentiation was observed in bioreactor cultures, as evidenced in the lower number of these markers in days 7-9 of the culture. Growth rate was very comparable in both in the bioreactor and in the static conditions. Concentrations of lactate in the supernatant of bioreactor cultures was lower than in culture dishes, probably reflecting to a better control in oxygen availability in the bioreactor. On the contrary, no difference was observed in the cell-specific ammonium production rate. Just to recap, we can say that the single-use stirred tank bioreactors has been successfully used for the erythroblast expansion. The scaling up of the bioreactor cultures from 0.5 to 3 liter using constant tip speed as a scaling parameter did not negatively affect the performance or quality of the cultures, measured in cell yields, viability, or expression of cell surface differentiation markers. And just to finalize, I would like to say that to be able to have 1 to 2 million cells per ml in 2.5 liters maintained for several days put us closer to the desired number that we need to a single transfusion unit.
Okay, great. So the first question is, are the constant tip speeds and PV methods still valid if the impeller type is different, like a Rushton versus a pitch blade? If not perfectly accurate, maybe it's close enough for small scale, 1 to 10 liters?
Most of the time, you would want to stay with the same type of impeller you're using in small scale and in large scale. The tip speed, strictly speaking about the physical forces at the edge of the material, will be accurate with a tip speed calculation, but a flat blade or Russian impeller creates much more dynamic mixing than a marine or pitch blade impeller, so the overall impact on shear is quite different.
Okay, and how do the calculations for scale-up change with 2 impellers? Do you double the diameter in the equation?
It depends on the equation. In the P over V, there is a term for the power number, and that, of course, depends on the type of impeller. So a marine or mammalian cell culture impeller will have a different power number than a Rushton, and it also depends on the number of impellers. So you would have that power number multiplied by 2 if there were 2 impellers.
And is shear from gas sparging more or less important than shear from tip speed?
That's a complicated question. Shear from gassing is an important factor. Bubble coalescing, for example, can impact shear stresses on the cells. So it depends a little bit on the bubble size and the quantity. But the stirring, of course, is a known source of shear, so that's one of the easiest places to start when considering how to scale up.
Okay, so it looks like we just have time for one more question. If we didn't get to your question, we will be passing them on to Anne and Cristina directly. So go ahead and continue to type in your questions. But the last question for the webcast is, why weren't the blood cells expanded in the rocker bag?
Rocking bags are commonly used in cell culture, but there will be a point where the amount of cells that you can grow in a rocking bag are limited because of oxygen transfer limitations. Also, for further scale up, it's very likely that a stirred tank single-use bioreactor will be needed. So it saves time and understanding if you can perform the research on the bench scale also in a stirred tank vessel.
Okay, well, thank you. And thanks to our audience for joining us. The recorded version of this webcast will be available for on-demand viewing on our website, and as a registered attendee, you'll receive a follow-up email providing you with a direct link. We look forward to having you join us for future BioProcess International Ask the Expert webcasts. Look for those announcements in your inbox. Goodbye.